Day 1 of Unit 6 is on something called Euler's method. It's not really connected to any of the other material we cover, but I threw it in Unit 6 here. We're going to start off with it. Euler's method is used to approximate points on the particular solution to a differential equation that passes through a point. So usually we have like dy dx is equal to x squared plus 1, and we have a point, maybe like 1, 5, and we want the particular solution that passes through this point. So we can say like y is 1/3 x cubed plus x plus c, and then you can plug in the point for x and y and solve for c. So you have the particular solution. And the ones we've done, as long as dy dx is only in terms of x, we can find that particular solution. Or if you can separate the variables, if it's something like this, you have to separate the variables and then you can find the particular solution. But sometimes you'll have a differential equation where we can't integrate this because it's x minus y on the same side. And there's no good way to separate your variables here. You can't like add y because now it's going to be y plus. And if you multiply by dx, you would have to like distribute the dx here. So there's no good way to find the particular solution of this. So what we do instead is we use Euler's method to approximate what the particular solution is. So that was a long way of saying that we're looking for the particular solution, but won't always necessarily be able to find it. So the way Euler's method works is we're going to start with a point. We'll be given a point. That point is x sub 0, y sub 0. And then you're going to be looking for a new point on the curve. To find the new x value, you take the previous x value and you add whatever our delta x is. And this is almost always given. To find your new y value, you're going to take the previous y value plus your delta x times the derivative evaluated at the previous point. So again, y sub 1, this is my new y value, is equal to my old y value plus our change in x, this is called the step, how much you're moving up by each time, times the derivative evaluated at the previous point. All right, so let's take a look at what some problems will look like. Example 1 here asks us to use Euler's method to approximate points on the particular solution of the differential equation below that passes through the point 0, 1. And it tells us to use a step of 0.1. It's telling us make delta x 0.1. So this is my initial point. 0, 1 is one of the points on my curve. We are going to go up by 0.1. So if I start my x value at 0, my first x value is 0, and I add the step, this would be 0 plus 0.1. So my new x value is 0.1. To get the new y, to get y1, we take the previous y value plus the step times the derivative evaluated at the previous point. So my new y value is equal to the old y value, 1, plus my step, 0.1, times the derivative at the previous point. So the derivative at the previous point, I would just plug the previous point in here, times -1. So my new y value is 1 minus 0.1. My new y value is 0.9. The next point would be, I'd go up by, I'm going up by 0.1s. So my next point would be 0.2. My new y value is equal to my old y value, 0.9, plus the step, 0.1, times the derivative evaluated at the previous point. The derivative at the previous point this time, it's always x minus y. X minus y, 0.1 minus 0.9. It's negative 0.8. So we've got 0.9 plus 0.1 times negative 0.8. So my new y value is 0.82. And you just keep going. 0.3, going up by 0.1s. My new y value is my previous y value plus my step times x minus y, the derivative evaluated at the previous point. So 0.2 minus 0.82. So I want to take that previous answer, add 0.1 times 0.2 minus 0.82. My new y value is 0.758. And you can do this as many times as is necessary. We'll do it one more here. So I go up by 0.1. My new y value is the previous y value plus my step times the derivative evaluated at the previous point. In this case, 0.3 minus 0.758. And I get 0.7122. So what this is giving us, these are not points on the particular solution, but they should be awful close to the points on the particular solution. So if I were to sketch those points in, we don't necessarily need to, but so we have a point at 0, 1, here's 0.1, 0.9, 0.2, 0.82, and so on. These points are not points on the actual curve. But they are points that are very close to the points on the actual curve. The further and further you go, the further it'll eventually get away from the points that are actually pass through this point and have a derivative of this. Most of the problems look more similar to this one. It gives us a point. F of 2 is negative 3. It tells us to use Euler's method, starting at x equals 2. We need 3 steps of equal value, and we are trying to approximate f of 5. So we're starting at 2, we need to get to 5. So we have to go 3 total units, and I have 3 steps. So 3 divided by 3 steps, my delta x should be 1. So my first point is given. I know f of 2 is negative 3. My delta x is 1, so I'm going to add 1 to my x. My new y value is the previous y value plus the step times the derivative at the previous point. So in this case, my new y value is my old y value, negative 3, plus my step is 1, times the derivative at the previous point. So f of 3 should be about 8. My step is 1, so I add 1 to my x. My new y value is the previous y plus the step times the derivative at the previous point. Oh, shoot. That was dumb. I did y squared plus x. All right, x squared plus y, x squared is 4, plus y is negative 3. My dy dx here is 1. All right, so f of 2 is negative 3. F of 3 should be about negative 2. Backtracking, sorry about that. All right, so f of 4, I added 1 to my x. It's the previous y value plus the step times the derivative at the previous point. X squared plus y. X squared is 9 plus y. F of 4 should be about 5. And to get my new y value, which is what I'm looking for, f of 5, I take the previous y plus my step times the derivative at the previous point. The derivative at the previous point is 16 plus 5, 21. So f of 5 should be about 26. That's what we're looking for. So hopefully this is making a little bit more sense. Let's try one more. It kind of has 3 parts here. It's the same type of problem. We're just going to do it 3 different ways. So on all of these, we are given a table of values here. The values that are given are the derivative of f of x. We know f of 1 is 20. And what we're trying to do is we're trying to evaluate f of 2. And again, we're going to do this 3 different ways. The first way is we're going to use a tangent line at x equals 1. So to write an equation of a tangent line, I need a point and a slope. Slope at 1 is 4. So y minus 20 equals slope times x minus 1. This is the equation of the tangent line. And we are trying to evaluate the y value when x is 2. Don't worry about that. I think I copied my cursor there. So our approximation is 24 using the tangent line. Problem with using a tangent line is it only takes into account what's happening at x equals 1 to approximate what happens at 2. Euler's method uses not only what's happening at 1, but what's happening at some values in between 1 and 2. Part B asks us to use a trapezoidal sum with 4 subintervals of equal length to approximate the integral from 1 to 2, and then to use that approximation to estimate f of 2. So trapezoidal sum, we're going to do 1/2 sum of the bases. So my bases are 4 and 4.5 times the height. The height from 1 to 1.25 is 1/4. From on this interval, my bases are 4.5 and 5, and my height is 0.25, and so on. And then with our calculator, we can evaluate what that trapezoidal sum is equal to. And we get 4.875. Remember, when you integrate from 1 to 2, this tells you this is going to give you the change in f of x from 1 to 2. So if f of x changes by 4.875 from 1 to 2, you don't Don't forget to add in the initial value. So that's the trapezoidal sum there. F of 2 is about 24.875. So that is a second way, if we're given a table of derivatives, that we can approximate f of 2. And the third way, which is what we just learned, is we're going to use Euler's method, starting at x equals 1, with 4 steps of equal size to approximate f of 2. So our 4 steps are going to be 1, 2, 3, 4. Looks like our delta x is 0.25. We know that our first point is 120. That is given to us right up here. So our second point is going to have an x value of 1 plus our step, 1.25. And our y value equals our previous y value. So the previous y value is 20 plus our step, 0.25, times the derivative evaluated at the previous point. Well, the previous point had an x value of 1. When x is 1, our derivative is 4. So at 1.25, our y value is about 21. The new y value then, so my new x is going to be 1.5. The new y value is the previous y value plus our step times the derivative evaluated at the previous point. Previous point had an x of 1.25, so the slope is 4.5. So my new y value is 22.125. New x at 0.25. My new y is the previous y plus the step times the slope at the previous point, which is 5. $23.375. And we do it one more time. X value is 2. My new y is the previous y plus the step times the slope at the previous point. $24.6875. Rounded to 3 decimals, 24.688. So notice all 3 methods give us answers that are pretty close, 24.688, 24.875, and 24. Of the 3 methods, using the tangent line is certainly the worst because it's just taking 1 point into account. I'm not sure which one would be more accurate, Euler's method or trapezoidal sum. Probably depends on what the values are. But that is Euler's method. That's all I've got for today.